Good afternoon, everyone. So we are the group 6.
So our topic today is using the distance formula in proving geometric properties.
The distance formula. The distance formula between 2 points, whether or not they are aligned horizontally or vertically, can be determined using the distance formula.
For example, let's consider your home location H from the mall M and visualize your situation in the Cartesian plane. Your location and the mall can be determined by naming the points in the Cartesian plane. The coordinates of a point is always written as an ordered pair x and y.
If your home is located at point 13 and the mall is at point 99, using the distance formula, find the distance from point H to point M. Let us substitute their coordinates first. We have d equals the square root of quantity x sub 2 minus x sub 1 squared plus quantity y sub 2 minus y sub 1 squared. So this is our distance formula. By substitution, this becomes d is equal to the square root of quantity 9 minus 1 squared plus quantity 9 minus 3 squared. Let's perform the operations next. This becomes d is equal to the square root of 8 squared plus 6 squared. If we square these two, it gives us d is equal to the square root of 64 plus 36. Adding these two gives us d is equal to the square root of 100. Finally, find the square root of 100, which is 10. So the distance from your home to the mall is 10 units.
Now, consider the points LA whose coordinates are x sub 1, y sub 1, and x sub 2, y sub 2, respectively. The distance between these points can be determined using the distance formula. D is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, or in this case, segment LA equals the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So this is our first example using the distance formula in proving the geometric properties. Triangle PQR with coordinates P is negative 3, negative 2, and Q is negative 1, 3, and R is 1, negative 2. We will show that triangle PQR is isosceles triangle.
In geometry, we have to remember that an isosceles triangle is a triangle with two congruent sides, meaning to say, we have to prove that in using the distance formula, we can find two sides of a triangle that has the same length. Let's start by illustrating it. Based on our given, P is negative 3, 2, Q is negative 1, 3, and R is 1, negative 2. We can see that if we connect these points, we are able to form a triangle, which we will prove if this is really an isosceles triangle. To do that, we have to find the distance of each side of the triangle. Since we are going to find the distance, we shall use the distance formula in solving. D is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. By substitution, let us first find the distance from point P to point Q. So this will be our equation if we have substituted our given. We'll let negative 3 as x sub 2 and negative 1 as x sub 1 and negative 2 as y sub 2 and 3 as y sub 1. Now that we arrive with this, let us perform the operations. Negative 3 minus negative 1 and negative 2 minus 3, and the result will be the square root of negative 2 squared plus negative 5 squared. When we square negative 2 and negative 5, we get the square root of 4 plus 25. And when we add, we have the square root of 29, which is the distance from point P to point Q. Now that we're done with finding the first one, let's move to the second one. Let us find the distance between points R and Q. Let us plug in our given using the distance formula. We let 1 be x sub 2 and negative 1 be x sub 1 plus our y sub 2 which is negative 2 minus our y sub 1 which is 3. 1 minus negative 1 is 2 and negative 2 minus 3 is negative 5. And when we square this, it becomes the square root of 4 plus 25. When we add that, it also becomes the square root of 29. Since the measurements of both sides are alike, PQ is equal to RQ. This implies that side PQ is congruent to side RQ, proving that it is indeed an isosceles triangle. Since it describes the definition of an isosceles triangle, hence triangle PQR is an isosceles triangle because it has two congruent sides. But we haven't solved for the third side yet. What if it measures the same as the other two sides? Well, it doesn't. Since side PR is horizontal, we can easily see that it measures 4 units, making it unequal with the other two sides, proving that it is in fact an isosceles triangle.
So let's move on to another example. Quadrilateral LOVE.
Coordinate L is negative 5 and negative 2. O is negative 2 and positive 2. V is positive 2 and negative 1, and E is negative 1 and positive 2. Show that diagonal of quadrilateral LOVE is congruent.
Before anything else, let us illustrate this first using the Cartesian plane. L is negative 5 and negative 2. O is negative 2 and positive 2. V is positive 2 and negative 1. And E is negative 1 and negative 5. If we connect the points, it forms a quadrilateral. So we need to prove that diagonals of this quadrilateral are congruent. When we say diagonals, those are the lines inside a quadrilateral that bisect each other. The lines that connect from point O to E and point L to V, so we need to find their distance and prove that they are equal. Using the distance formula, once more, let us first find the distance from point O to point E by substitution. This will be our equation. Our x sub 2 is negative 1 minus our x sub 1 which is negative 2 plus our y sub 2 that is negative 5 minus our y sub 1 which is 2. Then perform the operation so this becomes positive 1 squared. Since negative 1 minus negative 2 is positive 1 and this becomes negative 7 squared because negative 5 minus 2 is negative 7. Then square this which gives us the square root of 1 plus 49 or the square root of 50. We can simplify this by getting the square root of 50 which is the square root of 25 times the square root of 2 which gives us 5 square root of 2 which is the distance of diagonal OE. Now let us find the measurement of diagonal LV. X sub 2 is 2 minus x sub 1 which is negative 5 plus y sub 2 that is negative 1 minus y sub 1 which is negative 2. Perform the operations which gives us the square root of 7. Squared plus 1 squared, the result is the square root of 49 plus 1 which is also the square root of 50 which again if simplified gives us 5 squared root of 2. Hence, diagonal OE and LV are equal. This implies that OE is congruent to LV. Therefore, the diagonal of the quadrilateral is congruent.
Now let's move on to another example.
Triangle DEF has coordinates point D, which is quantity 1, comma 1, point A, which is quantity negative 3, comma 5, and point F, which is quantity 1, comma 5. Show that triangle DEF is an isosceles right triangle. First, let's find the measurement of side EF. So this is our equation. EF is equal to the square root of quantity negative 3 minus negative 1 squared plus quantity 5 minus negative 5 squared. Let's perform the operations. This gives us the square root of quantity negative 4 squared plus quantity 0 squared. Now we're left with negative 4 squared, which gives us the square root of positive 16, which is 4. So the distance from point E to point F is 4 units. How about side FD? So we have the distance of FD equals the square root of quantity 1 minus 1 squared plus 5 minus 1 squared. Performing the operations, this will become 0 squared plus 4 squared, which is 16. And the square root of 16 is also 4. Now, we can see that side EF is equal to side FD, which implies that they are both congruent. Initially, we would already think that it would turn out to be an isosceles triangle because it already has two congruent sides. However, let us prove further that here is really an isosceles triangle by also solving for the measurement of the third side, which is side ED. So we plug in everything and we let negative 3 be x sub 2 minus our x sub 1, which is 1, plus our y sub 2, which is 5, minus our y sub 1, which is 1. After performing the operations, we have here the square root of quantity negative 4 squared plus 4 squared. So squaring these gives us the square root of 16 plus 16. Add these and it becomes the square root of 32. And when we simplify, it gives us 4 square root of 2. So since it is not the same as the other two sides, this proves that we have an isosceles triangle. But we are also asked to prove that this isosceles triangle is also a right triangle at the same time. In order for us to do so, we must use the Pythagorean theorem. So our side ED would serve as our c squared since it is the longest side of our triangle, while the two sides earlier, namely side EF and side FD, would serve as our a squared and b squared. Let us substitute our answers. So 4 square root of 2, which is our ED, distribute the exponent which gives us 16 times 2, while 4 squared plus 4 squared gives us 16 plus 16. And when we perform the operations, we can prove that 32 is equal to 32. Since both sides are equal, we can say that the triangle is right because the sides satisfy the Pythagorean theorem.